The story of 20th century physics was a story of discovering many different phenomena. And the question was, do all these phenomena fit together? There were ideas like supersymmetry and string theory and so on. There were a whole collection of ideas which never really connected with the actual experimental observations that had been made. And there was sort of an attempt for a few decades to make that something that would be more explainable, but didn't work out. My own efforts really started from a different place. Rather than starting from the universe and trying to reverse engineer using mathematical ideas, what I was doing was using computers to run simple computational systems. Let's see what those things do, and maybe somehow we will see that those things behave in ways that are like the way that we observe our physical universe to behave. And the remarkable thing is that worked out. If we want to make something complicated, we typically imagine we have to go to lots of effort, have very complicated plans for what the thing is going to do. But what happens in the computational universe is that just all over the place, there are very simple sets of rules that are doing very complicated things. And it seems like a lot of questions that have been around for a century or more, we're starting to be able to unlock. I'm Stephen Wolfram. I've been motivated for a long time by understanding the significance of the paradigm of computation, both in its practical applications in technology and its implications for kind of deep conceptual issues in thinking about the world. Okay, so what is computation? It's the following of rules and seeing what happens. In fact, for me, the field of study that has to do with looking at simple rules and seeing what their consequences are, I've tended in recent years to call that ruleology, the study of rules and their consequences. Computation is a metaphor that is very useful because we're familiar with computers and how they work. Ruleology is really the core basic science about simple rules and how they behave. So for example, when we think about the whole universe, our current picture is that there's this kind of network of atoms of space, and the computation that the universe is doing is progressively rewriting that network of atoms of space, and doing that by saying, whenever there's a piece of network that looks like this, replace it by one that looks like that, and so on. When one's interested in kind of exploring the computational universe, there's kind of a question of what types of computations are most easily understood. And the one that I was sort of lucky enough to come upon at the beginning of the 1980s are some things that had a slightly different version of them, had been called cellular automata, and I kind of took that historical name. A cellular automaton is a row of cells. Each cell can be either black or white, for example, and the thing progresses, kind of making a picture down the page, line by line, and each successive line is formed from the one above it by taking each cell and asking what were the colors of that cell and the two neighbors of that cell, for example, on the step before, and then looking up some table to how that cell should be colored on the next step. The very simplest class I've tended to call elementary cellular automata, there are 256 of those. And over the last 45 years or so, pretty much every one of those 256 rules has ended up being useful as a model of something. My kind of all-time favorite is Rule 30, which has the feature that the numbers kind of just come from taking the number 30 and writing it out in binary, and that's a representation of what this rule actually does in terms of black and white cells and so on. Well, Rule 30 has this feature that you started off from just one cell and it produces this extremely complicated pattern. Some aspects of the pattern, it's kind of regular on one side, but if you look, for example, at the center column of this triangular kind of pattern, the center column, for all practical purposes, looks completely random. You can't predict it in any way. The only way you can find out what it's going to be, it seems, is by running Rule 30 and seeing what happens. It's kind of a little bit like what you get in something like the digits of pi. It's easy to say what pi is. It's the ratio of the circumference to diameter of a circle. There are methods for computing pi, but once you've computed it, 3.14159, etc., the digits of pi look completely random. And it's the same kind of thing with Rule 30, except Rule 30 is a much simpler kind of setup and one that is much closer to the kinds of things that you can expect to see in the natural world. So, what are some examples of natural systems that kind of can be described easily in terms of programs? One example, snowflake growth. Snowflakes grow by aggregating pieces of ice onto a growing structure. And there are very simple rules that describe the way in which a snowflake grows arms, and then the arms grow arms, and so on. Another example, in biology, lots of growth processes are fundamentally computationally quite simple. Whether it's the way that a mollusk shell kind of grows in a spiral, or whether it's the way the pigmentation on mollusk shells work. Yes, it really is the case that there's this kind of thing that is probably the secret that nature uses to make all this complexity that it makes, which is that in the computational universe of possible programs, even a very simple program can produce extremely complicated behavior. And that kind of led me to this concept of computational irreducibility that's been an important one for a lot of what I've done. Kind of this question of, when you have a simple program, if you want to know what it does, one thing you can do is just run it step by step. Let's say you want to know what it's going to do after 1,000,000 steps, where you can run those 1,000,000 steps and see what it does. The question is, can you jump ahead and work out what it's going to do without having to go through all those steps? We know there are certain pieces of computational reducibility. There are places in which we know there are irregularities in the universe, which we, with our finite minds, are capable of making use of to be able to say that's predictable, that's a law of nature, that's something that allows us to kind of reduce the complexity of the world to something that we can kind of tell a narrative about in our minds. When we start thinking about the world in computational terms, there's a question of sort of, what does that mean? People will say things like, if the world is computational, where's the computer that it's running on? This is a confusion. Models are a way of representing what the natural world does. They're not mechanistically what the natural world is doing. It's just the mathematical equations are a way of describing the way the natural world works. Now, the thing about the universe, it's like, how awesome is the universe, so to speak? And if we know the fundamental rules for the universe, does that mean the universe can't be awesome anymore? Does that mean we got it? It's all over. The reason that, in fact, the universe can still be, and necessarily will be, sort of fundamentally awesome, is this phenomenon of computational irreducibility. So, in a sense, you might say computational irreducibility is a bad thing because it limits what we can do in science. It limits the extent to which we can predict what's going to happen. But in some sense, computational irreducibility is what gives us any richness in life. Because if we could always predict what was going to happen, nothing is sort of achieved by the actual passage of time and the actual living of our lives. The fact that there's computational irreducibility means that sort of the living of our lives adds up to something. There will always be new things to discover. Within computational irreducibility, there are always an infinite number of pockets of reducibility, and each one of those represents some discovery about how things work. Each one of those represents a surprise. And then what becomes important is the sort of the human choice of which possibility to pursue. So within the computational universe, there's sort of an infinite collection of things that can happen that one can study. The thing that is the role of us humans is to decide what should we choose to find interesting. And it's been a very exciting journey last few years, kind of exploring those things. And I suppose from a philosophical point of view, one of the things that has most surprised me is that we're really being able to see kind of what is the fundamental machine code of our universe, what's sort of underneath all the physics we know. So at this point, I think it's fair to say this is sort of the paradigm that allows one to think foundationally about things. This idea that things operate according to rules and then you're looking at their consequence, that's a very general and very powerful idea.